Hi, this is Fazil Farooq from IIT Roorkee, and this is my project 2D Ising model phase classification using CNN. And under the course Fundamentals of AIML, submitted to Professor Mayank Goswami. This project uses machine learning to classify simulated 2D magnetic patterns from the Ising model into ordered or disordered phases. The 2D Ising model is like a miniature universe of tiny magnets on a 32 cross 32 grid. Think of it as a magnetic chessboard. Each square has a spin up or a spin down. At low temperatures, all spins align, forming large clean domains, and at a high temperature, they flip randomly, creating chaotic noise. We simulate thousands of these boards to study how order turns into chaos. So here we used Monte Carlo simulation and CNN. So for we used Monte Carlo, a random sampling method to evolve the lattice step by step until it reaches equilibrium. So for ordered phase, we start at t is equal to 1.8 and run 12,000 steps. And for disordered phase, we start at t is equal to 3.2 and run 5,000 steps. This gives us 16,000 snapshots, 800 for ordered and 800 for disordered. 1600, sorry. Uh, each as a 32 into 32 image. We label them as uh, 0 for ordered and 1 for disordered. So then we feed them into CNN and AI that excels at image recognition to learn the visual difference between organized domains and random noise. After training, the CNN correctly identifies 97.8% of unseen lattices. It doesn't use equations or thermodynamics, it just looks. We then scan temperature from 1.5 to 3.5. At each point, we generate a new lattice as ask the CNN, is it ordered or disordered? The answer stays 0 for ordered until t is equal to 2.2, approximately 2.27, then jumps to 1 for disordered. This sharp switch is the phase transition, and 2.27 matches the exact critical temperature which is around 2.269, exactly 2.269 from so the let's come to the introduction part. So this is the introduction of the project. The critical temperature is the of the 2D Ising model, which is precisely 2.269, where the system undergoes a second order phase transition. Below critical temperature, spins align into larger order domains, and above critical temperature, they become completely random and disordered. At exactly critical temperature, the lattice shows critical fluctuations with domains of all sizes. In this project, the CNN automatically detected critical temperature which approximately 2.27 by scanning temperature and observing the sharp switch from ordered to disordered predictions, matching the exact theoretical value without any prior knowledge. So here is the project objectives. So the first objective is to explore magnetic pattern. So in this simple 2D Ising model, we simulate lattices to observe how spin evolved from organized aligned states, which are large domains at low temperature, to chaotic random states. By visualizing domain formation, critical fluctuations, and thermal disruptions, we see the step by step melting of order, revealing the physics behind changes. So the second objective is build a machine learning system. We create a CNN that automatically spots patterns. Big blocks means ordered, noisy means disordered. It replaces manual calculations magnetization with AI-driven classification, achieving 97.8% accuracy during temperature scans. The AI detects the exact phase transition moment, flagging changes in material behavior faster and smarter than humans. And the third objective is to show how AI is helpful tool. This project highlights AI's role. So, this project highlights AI's role in simplifying complex physics through visual data driven methods, so no equation needed, by bridging physics and computer science, which is CNN here. And AI spots hidden patterns, detects critical temperature, which is approximately 2.27, which is matching to the theoretical value, which is approximately 2.269, and enables modern research, simplifying problems, visualize invisible effects, and discover laws from data only. So this is the we come to the methodology part. So this is Monte Carlo simulation. So we in this Monte Carlo simulation, which is a random sampling technique that mimics thermal motion. Instead of solving equations, we flip spins randomly and accept reject based on energy change, which is delta E here, which is delta E here. So and temperature, just like real atoms in heat. So at here at JNIT is Numba, which speeds up Python by 10x, and IJ are random spins to pick random spins, and delta E is the energy cost of flipping, which if delta E is less than or equal to 0, it flips to lower energy, and if the delta E is greater than 0, then it flips with expectation of minus delta E divided by T. So this is the data set. So here for ordered phase, we have temperature is equal to 1.8, and for disordered it's 3.28, sorry, 3.2. And we took sample of 800 for both, and 12,000 steps in ordered phase, and 5,000 steps for in disordered phase, with a lattice size of 32 into 32 grayscale image. So this is CNN architecture, and here the we have spin 1 plus 1 for white and minus 1 for black. So here we can see in the graph, for this we have plus 1 and for the black block it is minus 1. Okay. So here this is the CNN architecture. The input here is 32 into 32, which is the grayscale image. So and convo 2D, this is to scan for basic patterns, scan of edges as edges in spins, and max pooling. This shrinks the image, and this detects middle level clusters, and and uh, this further this further reduces the size, and convo D 3 by 3 identifies large patterns of full domains, and this is the final compression, and this flatten converts 2D map to 1D vector, and dense 256 combines features for reasoning, and dropout randomly ignores 30% neurons and prevents overfitting, and this we use this is the output probability, which is 0 for ordered and 1 for disordered. Hmm. So after training we get the final accuracy at 97.8%. Hmm. So hmm. We scan temperature from 1.5 to we scan temperature from 1.5 to 3.5, like slowly heating the magnet. At low temperature, which is less than 2.1, uh, we have 10,000 steps. Spin needs to form large stable domains, and near T is equal to 2.1, which is to critical temperature. We have 6,000 steps. System is critical, which needs balance, and when temperature is larger than 2.6, we have 4,000 steps already. It is the time when the system is already chaotic, and we no need to for longer runs. So So for each temp t, we run Monte Carlo for generation to generate equilibrium lattice. Feed to CNN gets probability, and if the it is greater than 0.5, then it is disordered 1, and if it is less than or equal to 0.5, it is ordered, which is 0, and then record phase, and then we record phase. A phase map versus T. So this is the result and analysis part. So here we can see in the left ordered, uh, in here it is the ordered phase. So the large black domains are large black and white are domains. So here the magnetization is 0.92 and energy is 1.88. Here the spins are aligned perfectly. So there is a large black number, and in this it is disordered, where with temp t is equal to 3.2, and random speckles magnetization is equal to 0.03 only, and energy is equal to 0 point, minus 0.71. uh, Spins chaotic, having no patterns. Here the CNN learns big blocks which are ordered and noise disordered. So let's come to the phase transition phase. Hmm. So here in the CNN phase prediction, we have this till this when the temp t is less than 2.27, the phase is ordered, which is the CNN prediction will be 0, and approximately at 2.27 the sharp jump to 1, which is sharp jump to 1, and then after 2.27 the it becomes disordered, and detected which is detected that 2.27 is the critical temperature, which matches exactly to the theoretical value 2.269. So in the graph second, we can read that below critical temperature, which is 2.27, magnetization is approximately is equal to 0.9, which is 90% spins are aligned in spontaneous order. So system picks one direction, up or down. So in the above critical temperature, which is above T is greater than 2.27, magnetization drops to 0, which has no net alignment. So thermal chaos wins, order vanishes. So at critical temperature, smooth drop due to finite size, classic order parameters in phase transition. So here in this red line is the critical temperature, which is 2.269. Here rise with the T. Low temperature spins are aligned with low energy, and at high temperature spins fight high, which is high energy. So king at T is equal to critical temperature, the slope changes sharply, like here, and hallmark of second order transition. So no jump, unlike first order, just inflection. And in the CNN training accuracy, read directly one blue line, this one, it is the training, it is for the train. The AI learns the training data almost perfectly, which is 98.7%, and the orange line value is 97.9%. Works nearly as well on unseen data, the final test, which comes out to be 97.8%. And hmm, so the discussion about this project was CNN was trained fast, stayed honest, which is 97.8%, and which is very reliable. And CNN learns physics patterns without knowing thermodynamics, and detects critical temperature automatically, works for unknown systems, 32 cross 32 grid, slide smearing. And on CPU, it was the timing was runtime was 11 minutes, uh, which is scalable on GPU. So the applications of this project are on material science, use CNN to predict magnetic phases in the thin films. Example, like hard drives and sensors. Uh, we need no to we don't need to measure, just image the surface, and AI says ordered or disordered. In neuroscience, brain activity shows pattern waves, like Ising domains train CNN to on neural recordings, detect critical states, example seizures and awareness. So on climate modeling, systems like ice melting, monsoons, or tipping points act like phase transition. AI scans satellite data, flags sudden shifts before they happen. AI in physics, data driven discovery, feeds raw experiment images. AI finds hidden order, critical temperatures, or new phases. No theory is required in this, and patterns reveal laws. So, the future work of this are for we can do this with larger lattices, like 64 into 64 or 128 by 128 with GPU, or 3D Ising model, which can real materials are 3D, not 2D, not exact critical temperature is known, so AI can discover it, apply to magnets, alloys, superconductors, and etc. So real-time phase transition prediction from experimental images. So we can feed live microscope or MRI data, and AI will output phase label instantly, which can be used in labs and factories and hospitals. And transfer learning simulation, real microscopy, train on perfect sims, etc. Explainable transferring learning from simulation to learn microscopic data. And explainable AI visualize what CNN sees in critical regions. And here we come to the conclusion of this project successfully demonstrated that artificial intelligence uh, understands phase transition 97.8% accuracy, detects critical temperature, which is 2.27, which matches exactly with the theoretical value, which is 2.269, and with no physical rules taught to it, learning purely from the images. And classical simulation plus deep learning, powerful combo. Monte Carlo, realistic lattices, CNN, visual pattern recognition, automatic, fast visual, no manual math. Tools for complex systems work on any lattice based model, scalable to 3D real data, live experiments, and replaces equations with data plus AI, and bridges physics and AI, new era data driven discovery. Uh, Physics provides data, AI finds laws, interdisciplinary future, labs, and codes, etc. So, this is the end. So, thank you for